Today we're going to discuss two topics in thermochemistry, enthalpy and entropy. Now we're going to concentrate in this first video on the concept of enthalpy. Now enthalpy is just a fancy word for heat. And when we deal with thermochemistry in chemical reactions, one thing we want to look at is reaction rate, how fast a chemical reaction occurs. We also think of this in terms of the collision theory when we're looking at how these reactions proceed. Collision theory, in order for a reaction to occur, I think of it kind of like a match with a matchbox. If we want a chemical reaction to occur, then first of all, that match must collide with the matchbox. I can wave it in the air all day long and it's never going to do anything unless I actually have the reacting particles collide. The more collisions, the faster the reaction. Also, I can sit there all day and just barely move the match head across the matchbox, and I'm still never going to get a reaction to occur because I'm not striking the matchbox with enough energy. So the reacting particles must collide with enough energy in order for the reaction to occur. Must cause bonds to break and new bonds to form in order for that reaction to occur. Also, I can strike the match really hard against the matchbox, come in contact, great, and it's never going to light if I have the wrong end striking the matchbox. I have to have the correct orientation. I have to have the side with the chemical scratching and striking the matchbox, or it's never going to react. So it must have that correct orientation. The molecules must as well. Now, factors that affect the rate of a chemical reaction, temperature. Think about it. The higher the temperature, the faster the particle is going to move, so you're going to get more collisions. All of these are based on collisions. Concentration. The higher the concentration, that simply means there are more particles per area. Therefore, they're going to collide more often. So once we get more collisions, we get a faster reaction rate. Now, the particle size or the surface area, the smaller the particle size means you're going to have a greater surface area for the same mass of material, because once you take a piece of matter and you divide it in half and divide those in half over and over and over again, you start subjecting more and more area to the other chemicals that are in that system. So those chemicals are going to be able to get to the substance more quickly. It's going to react more quickly. Now, a catalyst increases the rate of a chemical reaction, and the way it does this, and we're going to see this in a diagram in a minute, but it lowers the activation energy hump on whenever we're talking about how much energy it takes for that reaction to occur. And because it lowers the amount of energy we need to get the reaction started, it's going to increase the rate of the reaction. Now, catalysts are not themselves changed in the chemical reaction. They're involved in the mechanism, somewhere in the mechanism that makes the reaction speed up because it takes less energy. Now, we're not going to really talk about mechanisms for a few units from now, but I wanted to introduce this concept of a catalyst now because it plays into our reaction diagrams in a moment. Now, just because substances are mixed together does not mean that they will react. Whether or not a reaction is spontaneous, whether or not it is thermodynamically favored, is determined by two factors. One of these factors is enthalpy, and that's the one we're going to talk about in this first video. Enthalpy is the amount of heat, again, a fancy word for heat, gained or lost during a chemical reaction. We've seen these words before in Chem 1, but we're going to get this review now because we tend to forget. Endothermic, taking in heat, a chemical reaction in which heat energy is absorbed. Okay, the heat energy is absorbed. The products are higher in heat content than the reactants. Now, the container itself, think about it. If that chemical reaction is absorbing heat, taking in heat, it's got to take it in from somewhere. So it's going to take it from the container that it's being held in. And so that container is going to be colder since the heat has been removed. So think about that. Exothermic reactions heat exit. Heat is given off in this type of a chemical reaction. Products are lower in heat content than the reactants. The container, again, if we've got a system that's giving off heat, the substances themselves are lowering in heat content, but they had to give the heat away to something. They give it away to the container. So the container is going to heat up and be warmer since the heat has been given off to them. Reactions tend to favor the lowest heat or energy state, so exothermic reactions are thermodynamically favored, and that's very important to remember for some material that we're going to cover later. Exothermic reactions are thermodynamically favored. Now, how does this play out when we see this on a diagram? Let's look at this endothermic diagram first. In this endothermic diagram, we show where the reactants start out in energy. Okay, let's say this is 0 down here. The reactants start out at a certain energy. And as the reaction occurs in an endothermic reaction, the energy increases. It's being absorbed by the substance. And if you'll notice, this part right here, going up to that hump up here, is our activation energy. That's the amount of energy it takes to get the reaction started. That's the place, that's the energy to get what's called the activated complex formed. Now, the activated complex is just an intermediate substance. It's just a substance that's formed in between that's very unstable. And since it is very unstable, it won't last for long, but it's like the reaction has to go through that formation first before it can continue reacting and form the products then. And the products have this amount of heat here. So I'm going to draw a dotted line there just to emphasize that. Not a great dotted line, but it is a dotted line. And if you'll notice, that distance between where it started and where it ended up is called the heat of reaction, or the enthalpy of reaction. So enthalpy or heat of reaction. So if, for instance, this had started out at 10 and perhaps this was 40, then our heat of reaction would be 30 kilojoules, if we wanted to think about it that way. If we wanted to look at how much the activation energy was, let's say this is 50, we would say that the activation energy going from 10 to 50 would have been 40 kilojoules. So we're looking at that side scale for the amount of energy involved to determine this heat of reaction, which for an endothermic reaction is going to be positive because we're taking in heat. So if you want to talk about the potential energy of the reactants, if you wanted to draw an arrow, would be here. The potential energy of the products would be here. And again, that difference is our delta H, our heat of reaction. Now this activation energy here is going to be larger for an endothermic reaction because it requires a lot of energy just to get it started. So E sub A or E sub ACT, I've seen it written that way as well. That's our activation energy. If you want to look at all the way from 0 up to where the activated energy, or excuse me, activated complex is formed, that's our potential energy of the activated complex. So these are the kinds of things it's going to be asking you about on the worksheet and things that you need to know when you're trying to interpret these diagrams. So the potential energy of the activated complex is that green line I just drew. So now let's go down here to our exothermic reaction. In our exothermic reaction, we have the same situation. We're going to start out with a specific amount of energy of our reactants. So if you wanted to draw a line, this line from here to here represents the potential energy of the reactants. And our line from 0 up to here is going to represent the potential energy of our products. And again, that distance from where the reactants start and where the products end, that's our heat of reaction. Now think about it. This time we lost heat. We gave off heat. When we give off heat, by convention, this delta H value here becomes negative. Anything given off is negative. So that gives us again, our enthalpy of reaction, or our heat of reaction for that particular reaction. Now notice something about the activation energy for an exothermic reaction. Look at the activation energy here. When you look at that activation energy, that's not a lot of activation energy. E sub A or E sub ACT, either way, that activation energy is small. We still have that hump that has to be reached. That's still the potential energy of the activated complex. And think about something. If we reverse this reaction, let's say this reaction is taking hydrogen and oxygen and forming water. It's an exothermic process. What if we turned it around and said that this was a water being broken apart and turned into hydrogen and oxygen? Well, look what the reverse reaction would be. The reverse reaction for an exothermic reaction is endothermic. The reverse reaction is endothermic. So that means if we're looking at the reaction that we just looked at above, if we have the reverse reaction of that endothermic reaction, let's go back and look at it. If we go backwards, like we just did, the reverse reaction is going to be exothermic for an endothermic reaction. So that's just reversing that reaction and showing that they're just opposites. So what happens if we add a catalyst to the system? As we said before, the catalyst lowers the activation energy hump. I've seen them on the test, on the AP test, asked to draw in what the diagram would look like if a catalyst were added. And what it looks like is this. You still have the same delta H value. The difference is, look at that hump, it lowers the activation energy hump, and that's why it changes and speeds up the chemical reaction. So a catalyst lowers the activation energy hump. And look what else it changes. It changes the activation energy. It changes this arrow right here. So it changes that. It changes this energy of the activated complex arrow. So it changes that. So those are the types of things that are going to change when we add a catalyst. The activation energy, again, as I said before, as it says down here, for an endothermic reaction is considerably larger than for the reverse exothermic reaction. And the activated complex is just defining some terms I've already talked about. The activated complex, the transition state. It's got an unstable intermediate, as I said before, that has to be formed in the middle of the reaction. So, and this then again, just in words, shows some of the things that I already labeled. Heat of reaction is the difference between the products and the reactants. It's negative for exothermic and positive for an endothermic reaction.